Okay, hello everybody, and welcome to our March meeting and talk. I guess most of you are members, but a couple of guests, so welcome. And before I introduce our speaker today, let me mention that in April, we are moving our talk from the 16th of April to the 23rd. So make a note of that. And I'll send out a notice on that as well, of course, when we get closer to the time. Well, our speaker is Peter Gorovich, who is the founding dean of the School of Global Policy and Strategy at UCSD, and past chairman of the Political Science Department there. And he's going to speak to us about the challenge to democracy and the war in the Ukraine and how they are related. So we're really going to get a very, very insightful idea of what's going on in Ukraine and the global consequences associated with that and its meaning in the larger sense. So that should be very nice. Okay, so let me introduce our speaker today. Richard Carson is a distinguished professor of economics at UCSD, where he has been since receiving his PhD from UC Berkeley in 1985. He is past president of the Association of Environmental and Resource Economists. He was elected a fellow of the American Association for the Advancement of Science for his work on climate change and environmental valuation, and earlier served as research director for international environmental policy at the University of California's Institute on Global Conflict and Cooperation. He has worked on environmental projects around the world, ranging from the impact of arsenic contamination on groundwater in Bangladesh on its labor force participation rates, to tropical deforestation in Malaysia. He conducted the government's benefit assessment for the US Clean Water Act and its British equivalent. For the state of California, he worked on issues ranging from examining policies to increase electric vehicle penetration to design of strategies to enhance urban water reliability. He was the government's principal investigator for the economic component of the damage assessment of the Exxon Valdez and BP Deepwater Horizon oil spills. He's been involved in many large-scale forecasting exercises and won the Knowledge Discovery and Data Mining, KDD Cup, a major international forecasting competition. He is well known for his work on forecasting aspects of the demand for new products, including Boeing 787 Dreamliner, and was the chief scientist of Metrics, now part of Accenture, whose optimization software runs on the public-facing websites of many major corporations. Carson built one of the first large-scale bioeconomic models used for policy purposes that predicted recreational fishing behavior in Alaska at a fine spatial, temporal, and species scale. His work predicted correctly that China's CO2 emissions would surpass the US over a decade earlier than officially predicted, official forecasts, and fundamentally altering the path of international negotiations on climate. More recently, he produced county-level estimates of the role of US wetlands have played in reducing property damage from hurricanes and other tropical storms, and causally isolated the COVID-19 US temperature response profile, which I guess is what we're going to hear about today. The talk today is, why is the US being hit by wave after wave of COVID-19? A detective story with consequential twists and turns. Richard.
Okay. So let's take it away here. Where are we going? We always should try to get our bearings a bit correct. So I'm going to show you what actually happened, and I'm going to show you two things. This is this official sort of CDC numbers for the reported cases over the time. We start here effectively in mid-January, and we build. And the key thing here to note is that you don't really see the cases early because there was bad testing. And if we look at the cases here at the very end, driven by Omicron, you see these like little sharp upward spikes above the red line. And I will tell you right now that those are, that this actual pattern of data is impossible from an epidemiology standpoint. So we'll get to that in a moment. The death counts are sort of what people much more use to define the waves, because the typical assumption here is that the deaths are all accurately reported. So that was not the case early on, particularly with cardiac failure. But anyway, we get the first wave. It's going to happen pretty early, starting sort of in February. We get the second wave, which is technically what's called a rebound effect. We're going to have this giant third wave, which is going to happen during the fall and winter of 2021. It's going to deep way down here, where effectively the Biden administration is going to declare victory on July 4th. We're going to get what's sometimes called the fourth wave, sometimes called the fourth and fifth wave. If you call it the fourth wave, the first peak is associated with the Delta variant, and the second peak is associated with the Omicron variant. And again, this like little spiky behavior here is biologically impossible with this sort of pandemic. Okay. So what are we going to learn? First off, we're going to learn what infectiousness means along the way, and what you typically hear on terms, you know, the media talking heads are embarrassingly sort of bad and misleading. In the course of learning about infectiousness, we're going to start out with this quantity, which I think probably everybody's heard of, which is R naught, which is the expected number of infections that a single initial case called the index case generates. And we're going to talk about a lot of that. In fact, this talk is effectively going to be a talk about how R naught evolves over time. And that quantity is usually called RT, and sometimes effective R naught. So if we think about R naught, it's a stochastic number. That's why the term expectation comes into it. And we're going to learn something about super spreader propagation. We're going to learn about herd immunity, which is directly related to R naught. And as we move from R naught, which is the initial sort of condition, to RT, we can think about a couple things. We can first off think, what if humans don't do anything in response to this virus being there? And then between the first wave and the second wave, we're going to look at this notion of bending the curve, which received a lot of attention. And then we're going to learn about the factors, which I'm going to refer to as mobility, blocking, immunity, temperature, and variance, which are going to drive the actual path that's observed. So how do we think about R naught? Well, the way to think about R naught is that somebody randomly comes into your city, and they could live there, but somehow they've picked up the disease. Nobody else in the city has the disease. And so this first person who comes to New York City or Los Angeles or San Diego is known as the index case. Okay, when they come there, nobody's had COVID before. They don't know that they have COVID, so they take no precautions. And in which case you can think about what's the worst case disease here is when it's transmitted by people who are asymptomatic and it's airborne, and that's turned out to characterize COVID. So each of these index cases meets with what are called contacts. And it has a positive probability of transmitting the disease to each of the contacts. So we need some formal definition of contact. So what does the CDC uses 15 minutes of close exposure as a contact. And that's basically to fit contact tracing protocols. And so we'll define contacts in the same way. There's a big literature on defining contacts that we're not going to get into. It's this PT, this probability of transmission, which in the epidemiology statistics world is what you think of as infectiousness. So what is the expected R naught? The expected number of people that this initial index case is going to infect. It's how many contacts they have times the probability of transmission. The words expected are there because each person that you might choose to be the index case is different. So conceptually, and I should say, you can't really perform this experiment, but if I were to pick different people in San Diego, some of those people would have a lot of contacts, and some of those people would have few contacts. And so what I'm going to do is I'm going to effectively average over them. And some of those people are going to have higher probabilities of transmission just because they may have bigger lung capacity and can expel the virus more. And so I'm going to average over those. And then I'm going to try to describe how variable those are. So the first thing that should clue you in is that the average number of contacts varies radically by city. So at the same time, for instance, when the virus sort of first struck and Los Angeles was estimated to have an R naught of about 2.5, each person on average who had the disease in Los Angeles was initially infecting about 2.5 people. In New York, it was about 7.5. And that's driven because there's a higher contact rate. And when people looked at that, the contact rate is large, in a substantial part driven by commuting patterns. People in New York were riding the subways, and COVID clearly rode the subways. In Los Angeles, they were basically driving alone in cars, causing traffic congestion. But that made New York much more vulnerable because it was propagating a lot faster. Okay, so let's see exactly what this looks like. There are two different things. The simple epidemiology models assume that the index case, the random nature of infecting people is distributed what's known as a Poisson distribution. And what that means is that the average and the variance are the same. So this is pretty tight. And this is the Wuhan variant, which is assumed to have a 2.5. Every person on average, it affects 2.5 people. And you can sort of just see the bars here. The bar at 2 is biggest. It's a little bit asymmetric, which is getting you to 2.5. But now let's look at what are called super spreader dynamics, which is a different statistical distribution known as the negative binomial. With the super spreader dynamic, which clearly COVID has, the modal person actually infects nobody.
It doesn't work.
And what this means is that a virus that has this sort of super spreader negative binomial dynamics is much more likely to die out. And in fact, all these sort of investigations suggest that the sort of original Wuhan variant died out in lots of places. But once it gets established, it then has real breakout potential because it's infecting this sort of long tail. Now, keep these two graphs in mind and keep in mind that they're, that effectively, there's a tiny number of people infecting 8, but by the time you get out to 15, nobody's being infected. And here, there's a tiny little number of people at 15, but it's really small. Now let's move to Omicron, where instead of on average, somebody infecting, the index case infecting 2.5 people, they're infecting 7. Now you see the sort of Poisson assumptions looking very sort of normal-like, but look at the negative binomial case. I've got this little spike here because I put all the cases above 30 here. So about 2% of the cases here, index cases, are infecting 30 or more people. The most common thing to do is to infect 1. That's typically somebody in the same household. But the sort of second or third most common things are 0 or 2. But when you get down here and you have one of these situations, you can go from, a situation where you think you've got COVID under control to it having basically exploding really quickly. And sort of the biggest numbers out there are cases where hundreds of people have been infected by the same person. So how do we estimate R0? It turns out it's really, really hard because what? Nobody sees the index case typically. And there are a bunch of folks who do genetic sequencing who work on this, and it has some fascinating implications. The big problem is that if you're sitting here in San Diego, or in my little example here, Chicago, you don't know how many people actually showed up at your city. So these folks are known as the initial seeds. Once the virus is somewhere in the world, the seeds show up. It's well known here that the virus, that the first and second wave in the US were primarily driven by cases that came in from Italy and elsewhere in Northern Europe. And in fact, the most dominant variation in the genetic sequencing came back from Italy to Toronto, and then from Toronto, it spread to the northeastern cities. So how does this happen? You have a couple people who got infected in Italy. The government did something really stupid. It lined the people up in the O'Hare airport, which was fairly cold and very noisy, for 6 hours. And no doubt, in fact, if only 1 or 2 people were infected and they were standing in these lines, they probably caused super spreader events right there, amplifying what happened. So the problem with the R0 is that a large number of the positive cases are asymptomatic. They don't show symptoms, or they show mild symptoms, or they have symptoms that were initially confused with flu. That makes it really hard to do it. Because you don't, of all these problems, there are a whole bunch of methods that the statisticians have developed to try to estimate these things, and they effectively look at how fast things are doubling. But because you don't know what was there originally, this is just a really hard number to pin down. So if we think about the early information, the Chinese reported a number of numbers, sometimes an R0 just a little above 2. They reported somewhat higher R0. And the key initial Chinese failure was reporting that the disease was not airborne when it's clearly an airborne disease. The key US failure after that was not believing the Chinese when they corrected this and said it was airborne, and they also said asymptomatic transmission was an important part. And the CDC folks just didn't really believe this asymptomatic part, because influenza, which was their frame of reference, doesn't have that characteristic. Then a very interesting, strange event happened where there got to be a good estimate of R0. So what did you do? You had a single infected passenger board a big cruise ship known as the Diamond Princess on January 20th. They had mild symptoms the prior day. About 5 days later, lots of people on the ship were sick. The Japanese quarantined the ship. There were 3,700 people on board, a little over 700 tested to be infected, and that led to the initial estimate of R0 being 2.28. The early estimates assumed that everybody on the ship had the same probability of coming into contact with everybody else on the ship. It's called uniform mixing. That turns out not to be true. The crew, of course, has more chance of being in contact with the other crew and also being in contact with passengers. So anyway, there's lots of complicated modeling after the first one, the first estimate, and they're into modeling the traffic on the cruise ship and the ventilation systems and whatever. All of those estimates tended to suggest that the R0 was somewhat higher than 2. The CDC changes its estimate to 2.5 and suggests using an R0 of 4. That is, the difference, the index case infects 2.5 people. They said, well, it could be as high as 4. So when you're looking at what's doing, the other thing that you don't know is what's called the infection fatality rate. So how many people who get the disease die? What you typically observe is what's called the case fatality rate. So among the people who test positive, how many die? But what you're really interested in, particularly with asymptomatic cases, is this thing called the infection fatality rate. And so the original infection fatality rate was based on the 9 people who died like pretty quickly, and that gave you, said 1.3% of the people who get the disease die. And let me just say, that is like really, really high. I've worked on sort of air pollution illnesses, and this is sort of a fatality rate in the sort of 1 in 100 range. Typically, the government is trying to reduce risks that are in the 1 in 10,000 or 1 in 100,000 range. So this is a really big, this is a massive risk. And not surprising given this sort of risk factor, COVID's going to move into the 3rd leading cause of death in the US after heart disease and cancer, which is a shocking thing to do. So people have worked in this area. We work on reducing air pollution. We've gotten the death counts from air pollution from 100, 150,000 down to about 50,000. And the same thing on deaths from automobile accidents. Those have drifted down from 150, 100,000 to about 50,000. So let me just say, we're talking about a massive change to the structure of US death with COVID. So anyway, the death count increases over time. It raises this rate to 1.9. There's a big debate over the infection fatality rate because you don't know how much of an age structure there is in terms of the fatality rate. So if you looked at the Spanish flu in 1918, it actually mainly killed younger people. And that's going to turn out because the old folks had some memory of a variant similar to the Spanish flu decades earlier. But anyway, the passengers were older, but they were in generally, much better health. And the crew was generally quite young. You've got the captain and some other old folks, but cruise ships are made up of young folks in terms of the crew. Once you know the R0, you immediately know how many people are going to get infected before the pandemic ends. And that's called herd immunity. So what is herd immunity? Herd immunity is equal to 1 minus 1 divided by R0. So if R naught is equal to 2.5 people being infected by the index case, the herd immunity level is that 60% of the people are going to get infected before the pandemic comes to an end. And so the whole game that's going on here is how are we going to reach herd immunity? Because viruses, a virus with an R naught of 2.5 is going to expand the number of people it infects until it hits herd immunity. And there's, that's just going to happen. So let's see why this is true. If we go back to R naught equal to contacts, remember, we're making this really easy. So we've got 100 contacts and each contact has a 2.5% chance of being infected. So what's going to happen if 60 of those contacts are immune to being infected because they've already been infected? What is RT? This is sort of the current value of R naught is going to be equal to 100 minus the 60 times the 2.5%. And this is going to give you an R naught of 1. One case of COVID is going to produce one other case of COVID. And as soon as your RT drops below 1, the virus starts to die out. It can take quite a while to take it out. But in other words, this is how the fact that you know what R naught is means that you know what the herd immunity level is. And it's simply, it's basic high school math. It's just, you've got fewer people to infect. And when each current case of COVID can only infect fewer than one case, then, that just sort of is the mathematical definition that it has to die out. Okay. Once you know the herd immunity level and you know the infection fatality rate, you know what the expected death count of the virus is. And so, I mean, if we go back up here, this this is sort of by like, the end of February, this is what the government was staring at. So for the US, the expected death count was 2.6 million people. And that's because the population is 331 million. The herd immunity level is 0.6. And we're going to use the lower range of the infection fatality rate of 1.3%. If we use the higher range, which most people, the 19 people dying was sort of the better answer, then instead of looking at 2.6 million deaths in the US, you're looking at 3.8. So that's when Trump said that he had saved millions of people by restricting the flights from China, this was the basis on which this was doing. Supposedly you had kept out COVID largely out of the US, but the fact that COVID basically came back into the US from Wuhan via Italy meant that you were still looking at exactly this calculation. And other countries looked at it. China stared this in the face and saw that they were looking at a loss of 10 million people. The British Prime Minister, who was all for letting this sort of run wild, finally got convinced when when his science advisors sat him down and said, look, you're looking at more than 500,000 people dying in a reasonably short period of time. So you would think this should freak out any rational policymaker. So let's think about some simplifications. In the epidemiology world, the models that are used are known as Seer models. You take the number of people who were susceptible to getting the disease. That starts out to be initially everybody. You look at the process by which they get exposed. You look at the period during which they're infectious. You look at who can no longer get infected, either because they have immunity or they're taken out because they've died. The underlying math here is just some fairly simple differential equations, but I suspect nobody wants me to go into those. And what do epidemiologists work on? They work on how different identifiable segments of the population mix with each other, because that influences speed. I'm going to really simplify a huge amount of this by getting rid of lots of the complications. I'm going to assume that there's a 10-day period where people are exposed and can get infected. That's not doing a whole lot of violence to the reality. We're going to ignore the early messy period where the virus has a good chance of dying out on its own. And we're going to ignore a whole bunch of issues on how the virus slows down at the end, because this uniform mixing assumption gets to be important, because if you have big pockets of, at the end, for instance, of people who aren't vaccinated, you can get the virus going for a lot longer. In sort of math terms, this is known as local linearity. All you're going to need is some basic high school algebra to get a good approximation to the actual intuition. Okay, so what happens if without a human response? Well, the virus just continues to go until herd immunity's reached. The rate increases sharply, then it's going to decrease as you approach to herd immunity. The length of time is going to depend on these, this infectious period, this length of time between the current infection and the first one it causes. It's going to turn out that both of those are reasonably close to 10. And it also is going to turn out that while you don't know this initially, after a while, you know this fairly well. And why is that? There are a lot of great studies out there where medical schools were swabbing all the personnel daily. And that allows you to sort of pin this down without having to do it in the actual data that people like I am observing, and that's really good. And just to say, this is very different than a lot of diseases. So, for instance, HIV has an R naught somewhere between 2.5 and 5, but it has a tremendously long infectious period after people have it, and that means this sort of careful modeling of the transition from one state to another is a lot more important. Okay. So what does exponential growth mean? That means that if the index case is going to infect 2.5 people in 10 days, and you can see my simplification. If I were really taking account of this, I would say, well, almost nobody's going to get infected in day 1. Almost nobody's going to get infected in days 9 and 10. That was why the CDC recently cut back on the quarantine interval. People start to get infectious on day 2. Infectiousness peaks typically on day 3 or 4. But anyway, we're going to ignore those little niceties. So the second generation are 2.5 people on average who got infected, are each going to infect 2.5 people, and so you've got 6.25. In the third generation, we just keep multiplying the 2.5s together and we get a little over 15. This is just the usual, you raise things to the R naught to the kth power. 10 generations out, which the 10 days is really convenient because 10 generations is 100 days. We have expected about 9,500 people to be infected. And that just seems really small. And that's the key sort of to understanding this. 200 days out, our 9,500 people have infected 90 million people. And by the end of the year, everybody on the planet has been infected multiple times. So that's what exponential growth that you don't do. And this is sort of a graph. This is an R-naught. We make the assumption that there are 100 initial people who came over from Europe who were infected. And this is the path that you would get. So you churn along here, this is sort of in the thousands, and at some point, this just turns up really steeply. That obviously didn't happen, but let me show you what happens. We're going to use a higher R-naught. The low end of Delta and Omicron's 5. And so what happens if you have a higher R-naught, you reach this point where you sort of turn up and get explosive growth much quicker. So what that says is that the Wuhan variant, it was not near, if Delta and Omicron had struck first, it's hard to imagine what would have happened. Just because you had so much longer to sort of prepare with the Wuhan version. Okay, so anyway, we obviously didn't take that path. Why didn't we take that path? Any rational decision maker looking at the notion that you're about to kill 2 to 3 million US people in the US tries to do something about it. About the only thing you can do initially is the lockdown. This was used by China successfully. It was used later by a number of other countries ranging from Taiwan and Vietnam to New Zealand, but the US didn't do that. And that's because the lockdowns in the US weren't comprehensive or long enough to stop it. So why couldn't the US execute this? The big thing is it didn't know where to lock down. So, I mean, if 100 days into the virus, we're only looking at less than 10,000 people scattered across the US, you don't know where they are. And without testing, the big thing that China logistically figured out in a really draconian way was how to supply the people at lockdown in all these big apartment blocks with food and other things. And there was clearly not the political will in the US for that sort of lockdown, even though it's pretty easy to argue in retrospect that you might have saved 1 million lives. Okay, so how do lockdowns work? Well, remember our R-naught formula here is just contacts times the probability of transmission. So what does a lockdown do? A lockdown simply reduces contacts. And so we could write our current RT as contacts at time t times the probability of transmission. You don't really observe this very well. It turns out what the modeling community uses is cell phone mobility data. So a company called SafeGraph and a couple other ones made available records on how many cell phones are moving around and where they're moving around and whatever. So usually you take whatever the initial contacts were. Remember, the probability of transmission hasn't changed. And so we're just going to multiply the contacts by this mobility factor. And so if mobility is going down, the number of effective contacts is going down. So if we think about this, mobility dropped in the US roughly by about 60% in the early lockdowns. And what does that do? That basically, if mobility drops 60%, MT is 1 minus 60%. So what that's going to do is that's going to put the current rate at which the virus is infecting people down to about 1. Okay, so that each infected person is only infecting about one other person. And so that's you're going from this exponential growth at 2.5 to something which is just basically reproducing itself. And the difficulty here is, even if you drive RT close to 0, what's going to happen if you let your foot off whatever the restrictions are and MT rises? What's going to happen? RT is just going to go right back up. So there's nothing magical about squashing it to begin with. If you let it up, it just does what it wants to, does what it naturally does. So what do you do after an initially insufficient lockdown? And so the US was not alone in thinking about having an insufficient knockdown. Well, the big thing you then confront is, hey, there's another factor out there, and that's the fact that if I overrun and exceed my hospital capacity to take care of the really sick people, then the infection fatality rate is going to go way up. And they were completely freaked out by what they were seeing in New York, because the case fatality rate was 9.2%. That meant that if you tested positive in New York through June of 2020, you had almost a 10% chance of dying. Okay. Almost nobody has seen something that's killing off 10% of the people who are getting infected. That's just, there are some things that do that. They're usually sort of in the biological warfare sort of category. So people knew that the 9.2 rate was high, because what's going to happen, the difference between the case fatality rate and the infection fatality rate is, the infection fatality rate is all the positives, and the case fatality rate is only the important ones. And you knew that a lot of the people who were asymptomatic or mildly had mild symptoms weren't being tested along with the asymptomatics. But this really got, this really brought some attention. I mean, at a number like this, you're looking at more than 10 million dead. So what else does a lockdown does? Supposedly a lockdown buys you time to implement testing, reporting, put into place contact tracing, increase medical capacity, and basically plan for what you know is going to happen. This turns out to have been a fiasco of epic proportions in the US, the failure to get this down. And if we look at the better success rate of a number of the European countries than a number of the Asian countries, is that they did the right thing after they got hit, after they had the initial lockdowns. Okay, in the longer run, reducing the speed of how the virus is going to burn through the population gives you time to develop treatments, and it also gives you time to develop vaccines and to vaccinate the public. And so what you're doing in some sense is you're saying, hey, the more I can slow the virus down, I'm going to reach herd immunity through vaccinations, and I'm going to reach herd immunity at a later date when I know how to treat the people better, so I don't lose nearly as many people. Everybody probably remembers the term bending the curve from nightly TV. So bending the curve is what you do after an initial insufficient lockdown. You realize that you don't want to you realize that you drive up your infection fatality rate pretty high once you can't treat the people. And there are two versions possible. One often referred to as the yo-yo response. Basically, things get really bad. The government implements some type of measures to drive down the positive case rate. At some point, cases in the hospitals stop being overrun and you relax restrictions, and you just keep doing that. The government can either impose these restrictions, but for all the crazy people who said, hey, let's just let this run wild and get it done as quickly as you can, it turns out that, and unfortunately had too many of my economic brethren who at least early on made that sort of statement. The problem is that you can't do that. As soon as the people see the hospitals full on TV, they naturally slow down their contact rates and do other things. And that's caused a endogenous public reaction. And so we were looking at planned visits to different sorts of retail establishments in the state of Washington, and what you saw there was that as the fourth wave started to sort of grab hold, people were cutting back on their planned visits weeks before it got really out of hand. If you really had control over things, you could hold the positive capacity right below where it would overrun the hospitals. You let the targeted number of cases increase as you get the medical capacity up. And this is the quickest way to achieve the herd immunity without driving the death count rate up. But anyway, nobody's actually figured out how to do this. Okay, so let's think about the second wave. We're going to have a classic rebound. People are going to increase their contact rates. We're going to get widespread use of what I'm going to call barrier methods, because they all work in the same fashion. If you social distance, you're putting a barrier, a sort of distance. If you wear different types of masks, the masker the variants. If you put up plexiglass shields, those are barrier methods. If you use ventilation to keep the virus from spreading, those are all barrier methods. So anyway, they work in exactly the same way as contact reduction. So if we let the barrier method equal 1 when there's no transmission stopped by the barriers, and equal 0 when it's all stopped, the current rate at which the virus is propagating is now going to be just equal to BT times the mobility factor times the original contacts times the probability of transmission. So it's really just that simple. You've got two ways to reduce contacts, what we would think of as effective contacts. You can have a barrier, or you can reduce the actual number of contacts by doing those. And to a first simple approximation, it's just a multiplicative factor. What this means, though, is that it's really hard, for instance, to separate out what actions to reduce mobility are from actions to get people to wear face masks, or actions to do social distancing. And that's because they all operate, they're all influencing the current rate of transmission in the same way. And so what do you have to do there? You get some natural experiments like Kansas, where anyway, the governor puts in a mask mandate and the court overrules it, and about half of the counties roll it back. And then you can see that masks are actually, pretty effective when you do that. So that's a natural experiment. What we don't do is we don't get what you would think that this sort of yo-yo effect would produce. And that just says if you have a pure yo-yo sort of effect, you have an initial big spike, you go down, you let off the brake, it goes back up, you let off the brake. So why is it doing, what's happening is it's dying out. So it's effectively dying out because you're infecting more and more people over time. But if you saw what I showed you at the very beginning, this is of course not at all what happened. Indeed, the third and fourth wave peaks are dramatically higher than the second wave peak. So one way to think about this is that the US basically is flying blind, because the CDC and most states have almost no clue with what's actually going on. And I will say in the CDC's defense, it's not that they were unaware of these problems. So the problems stem from the fact that the US has this bifurcated system and the states are actually in charge of reporting the data. And so what happens is sometimes the states every day report deaths and they report cases, and you see those on the news. However, the deaths that the states report, sometimes those deaths occurred the same day, and sometimes they occurred months earlier. Positive cases, sometimes they're the same day they were returned, oftentimes they're weeks later. And they're reported by not the date that they were administered on, which is what you would want to know if you're an epidemiologist, but the date at which they were returned from the lab. And that's just pure insanity. I mean, the date that they're returned on the lab, if they're returned weeks later, is like useless for every sort of purpose you can imagine. And indeed, if you don't get them back in a day or two, you can't do contact tracing. It got even worse. The states were gaming the system because the CDC had some of the suggested measures for barriers and mobility that were driven by what was called your positivity rate, what fraction of your tests were coming back positive. And so a bunch of the states started doing antibody tests, which meant that you were testing whether or not you had been infected in the past. Well, all of those tests basically produced a negative result. So they were driving down their positivity rates in a way that made absolutely no sense. The surprising thing is, and in particular, if you look at some of the other sort of surveillance things, the government during this time period mounts no big surveys to try to figure out what's going on in the population as a whole, which would have meant surveying tens of thousands of people and swabbing their noses and whatever. Anyway, the reporting basically, the data is so bad that you can't do much with it to intervene before spikes do it. And the CDC, in a really messy notion, tried to switch to hospitalizations because it realized that what the states were reporting was almost complete garbage. Let's look at the state of Florida to give you some indication of what was actually happening. My research group rebuilt the death counts based on death certificate dates, which is a criminal offense to falsify, whereas the reporting requirements, if you reported death a couple months late, that's nothing wrong with that. So anyway, on the left side here, the blue bars are what the state reported of Florida reported daily. The actual deaths are in red. And if you just fit sort of a very simple model to it, you can see that you've got an exploding sort of peak here. And, the state basically thinks that very little is happening. Florida looks bad, but it's got plenty of cousins, Arizona, Georgia, Texas, a whole bunch of states. There are some states actually that look really good though. For instance, the death counts in Michigan and the reported and actual death counts in Michigan are almost identical. So there's no reason that you can't do this. And we caught onto this problem actually in a state that has good reporting, Massachusetts. And what we could see is Massachusetts, the reporting got bad as the cases went up. And as a statistician, that's the worst possible thing, because just as you're trying to eke out the signal of what's happening, the reporting is deteriorating at the same time as the public health infrastructure is getting overwhelmed. So this is the University of Washington's Institute of Health metrics model. So the actual daily dead is on the vertical axis, their predictions on the horizontal axis. The 45-degree line is what you would get if you had a perfect fit. And this is the model that got reported almost every night on nightly news channels, and the model that after a while everybody was paying the most attention to. So after we reconstructed the death counts, the UCSD model are the black dots. It turns out that the University of Washington's model was explaining about 66% of the variance. Our UCSD models explaining about 97% of the variance. To put that in a different way, on average, the University of Washington model was off by about 25 deaths per state per day, at a time when you're running maybe 400 or 500 deaths. That's pretty close to unusable for most purposes. And our model's off on average by about 8 deaths per state per day. So it's like a radical different change. And so does this have anything to do with the fact that I am a really good statistical modeler? Nothing. It has everything to do with the fact that once you go back up here and you look at this data, it's just, you know, in lots of states, it looked like textbook classic stuff. And so anyway, this generates something that's fit very well. Okay, so we have a hopeful late summer 2020. The Chinese leader Xi had told Trump that the virus might die out with temperature. Anyway, things start to drop in the summer. The experience from elsewhere in the country suggested that the worst case New York, you know, 9 people dying per 100 or 4 people dying per 100. It was sort of in this 1% to 2%, which was the sort of consistent with the Diamond Princess. Was it? So, you know, that said, this sort of ruled out losing, you know, 10 million people. There's more testing. New York did the country a tremendous service by figuring out how to reduce the fatality rate. They did very interesting things. They figured out that putting people on oxygen was often better than putting them on ventilators. And anyway, they learned all sorts of things, and that actually spilled over to the rest of the country and sort of drove this down. The Trump administration then gets into crazy and a sort of what will go down in a really dark history for Stanford. Scott Atlas, who was one of their, became Trump's main COVID advisors, and several other folks associated with the right wing put out what was known as the Great Barrington Declaration, which said, let COVID rip through the population as fast as possible, other than trying to protect people in nursing homes, which turned out not to work anywhere. And then the Trump administration does the usual thing that almost all administrations going into an election does, is they try to pump up the economy. And with the economy in partial shutdown, that means doing everything you can to get contacts going up. I'm going to say this is not going to turn out to be, in the end, good for the academic community. The academic community really got behind, particularly the epidemiologists, got behind what they thought the lessons from the 1918 Spanish flu were, and that was that the cities that implemented barrier methods and tried to do social distancing really reduced some of the impacts. You could compare cities like St. Louis and Philadelphia and whatever. It's going to turn out that the US academic community is entirely going to be blind to the fact that this is a temperature-driven situation, and they can't see the temperature from the 1918 Spanish influenza because, again, the reporting is too bad. And there's a British paper, though, in the Journal of the Royal Society there, which shows that even in England, the temperature is the second factor, and they say if we had better data, it might well be the first. And the studies on influenza would say that influenza is almost an entirely temperature, humidity driven virus. The academic community was also sort of enthralled with machine learning and data mining. This is going to turn out to be a disaster because you don't have enough data. And if you've got a temperature-driven phenomena, you just don't see the temperature. So too many things are changing at the same time. And so what are the machine learning algorithms doing? They're learning the perverse ways that the states report the data. For instance, you can show that deaths predictably fall every Monday, and that's because a lot of the office processing information are closed on Sunday. So anyway, this is going to be bad. We also had a bad case of sort of political correctness here, where it was clear that the minority population was dying at a much higher rate, and there was a tendency to ascribe that to either worse medical treatment and or higher rates of pre-existing conditions. And when people have looked at that, the main thing driving this minority population was indeed dying at a much higher rate, but it's mostly being driven by higher contact rates. And that's because they were the backbone of the essential workers. And if that had been the focus of the analysis, you would have seen that once you let off the brakes on the contact rates, that things were basically going to explode. And that it's, you know, and all this is saying is, hey, this is basically a temperature contact rate, affected contact rate story. Little else going on. So the third wave is going to involve the needless loss of 200,000 Americans. And why is that? We already knew by early October that the vaccine trials were wildly effective. They had high efficacy, few side effects. You had something called Operation Warp Speed that was thought to roll out the vaccine quickly. And anyway, so you started, the Trump folks started encouraging large-scale rollbacks of measures to reduce contact and block transmission. And then big holidays, Labor Day, November, Thanksgiving, Christmas, New Year's, all of these things basically trigger big increases in contact rates. And predictably, several weeks later, you start to see the peaks from those come about. So it's not that the epidemiologists were completely asleep at the wheel on temperatures. Some of them knew, you know, clearly flu. The thought was more people inside or in closer contact. Also turns out that the virus itself has lots of biological characteristics that are tied to temperature. For instance, how long the virus stays alive in the air is a function of temperature. and how well it's able to penetrate your nose is a function of temperature. Anyway, the University of Washington folks, there was a paper in Science that showed there was the flu monitoring system picked up these things. So they were less asleep at the wheel in terms of this. So let's see. I've said this already. A virus that's temperature driven is sensitive to the temperature. What that means is that there's not a single R naught, just like every city has a different R naught because of its contact rate. Every temperature with a temperature specific virus does it. And one of the things that pulled the epidemiologist off the trail of temperature was there were tons of studies done, this is like everybody's a backyard epidemiologist, with the wave 1 COVID statistics, but they were just too bad to actually pin things down. And so anyway, I have a paper where we estimate what's known as the temperature response profile after we correct the death counts and come up with a way to control for differences in testing. This looks just like an agricultural production function where you're putting in fertilizer and water, and temperature is one of the inputs, and you observe the outputs daily. You have some idea of what the lag between the inputs and the outputs are. And what you can think of this model is just effectively saying, how does RT change with changes in temperature, controlling for a bunch of other things that could be altering how RT is changing. So this is the temperature response profile for deaths. You pick some number as the reference temperature. Here we pick 31 C, which is the midsummer US average. That's 89 degrees Fahrenheit. And 5 degrees C here is about 42. The way to interpret this is if you were expecting to see 10 if you were expecting temperatures when you saw 10 cases the past week, or I should say 10 deaths the past week, generate deaths next week, if you were expecting 10 deaths at 31 C, by the time you got to 5 C, you would be expecting 15 deaths. So that's a 50% increase. And that's just how to read this. This is saying, as you move from here to here, your death rate is going to go up by 50%. You would expect positive cases to be much more sensitive. And why is that? The deaths are occurring largely amongst old people who are not mobile. And this is really frightening. This is saying that if at 31 C you were expecting 10 cases, by the time you get up here to 5 C, you're going to be expecting about 40 cases. So it's a huge increase. That's just massive temperature amplification. So what's another source of fuel is then we start getting variants in. And so what do the variants do? The variants increase the original R naught. And I will say the variants were totally expected. They could see them happening. They typically saw them elsewhere. What the variants did was provide a huge amount of media hype to all the talking heads on TV. And the notion of the variants often masked the fact that most of the effects were being driven by temperature and not the variants per se, and we'll see that in a minute. So what do variants do? Variants, just from an evolutionary standpoint, they tend to become more infectious. That is, they increase TP, or they evade immunity via prior infection. And this isn't going to be a large factor until Omicron. Okay, so what can we now represent RT as? Well, remember, we've got RT is equal to barriers times the change in mobility times contacts times the transmission, or that should be a P. This is bad. No, well, I think earlier I used PT, but anyway, this is the transmission probability. So what's going to happen is that both temperature and variance modify the transmission probability. So what are we going to do here? We're going to modify the original transmission probability by the temperature response profile, which I'm going to represent as TRP, and what the variance scale factor is. So if the original Wuhan version was 2.5 and alpha's 4, then that means that VT is going to be 4 divided by 2.5, so 1.6. So now we have pretty much a complete representation of what's going on. You've got, effectively, you've got the current rate at which people are being infected is a function of the barriers you're deploying, the change in mobility, the temperature amplification, and the variant amplification. And we have one more factor. The last factor is how many people are susceptible. So originally, you could think of this as immunity. The susceptible is just sort of 1 minus immunity. Initially, everybody's susceptible. One way to think about this is that we may have infected about 10% of the population during the first couple waves. So that's saying we need to have one more factor, and we're just going to multiply it out, and it's going to enter exactly in the same way as barriers and mobilities. And so anyway, this is the 1.6 that alpha represented. There's a dynamic factor, and the dynamic factor is a fascinating sort of take on this. This is the state of Georgia. We give people an initial number of cases. You're generating rates at above RT equal 1, so it jumps to 17. We hold the temperature fixed for a little while because that's what happens in Georgia. And then the brown line goes up, and the brown line goes up, and this is just this curve right here. So it's going to go up by 50%, but this blue line, which has a different axis, much more deaths here. And you can see the difference between the brown line and the blue dash line here. How good you are from a policy perspective is where you're going to fall between the brown line and the blue line. So if you follow the brown line up, you're going to end up, with 25 deaths a day. If you follow the blue line up, which happens if you don't keep the death counts under control as the temperature changes. So the key thing is the temperature's amplifying things. And so if you want to keep the case counts and death counts under control, as the temperature falls, you have to implement more and more stringent measures to increase barriers or decrease mobility. So what this says is if you basically ignore the fact that, it's exploding and every week you've got more and more cases and deaths, you're going to end up with 415 deaths a day instead of 25. So we did this out of sample forecast in the middle of the summer. This is sort of pre-calculus maybe. So we're going to take the ratio of the cumulative positives. So this just says however many cumulative positives you had in mid-June, and that's going to be the denominator, the number of positives you had in mid-December, that's going to be the denominator, and then we're going to take the logarithm, and we're going to do that for how the temperature response profile is changing. Theoretically, you predict that you should get a straight line with a slope of 1. So that was our regression prediction here that we did in mid-June. The states then filled in what actually happened. So temperature alone explains 40% of the variation in how the third wave unfolded. If your eye is really good, you can see that most of the states below the line were controlled by Democratic governors. And the few instances, there are 4 states where the Republican governors openly split with Trump: Vermont, Massachusetts, Maryland, and Ohio. And almost basically the Utah governor didn't criticize Trump, but said separately that what he was saying was wrong. All of those states actually do a really good job. In fact, a better job than the Democratic governors on average. So anyway, about 40% of the variance is explained by temperature. About 10% of the variance is explained by the political leadership of the state, and about another 10% of the variance is explainable by differences in things like face mask adherence. Okay, so wave 3 is going to end. The Biden, as the weather warms, the Biden administration is going to help sort of do this. When it comes into office, it's going to drive down BT and MT in a whole bunch of different ways. BT from face masks to ventilation. It's going to drive MT down by giving out large unemployment benefits, which encourage people to stay home. The vaccine starts to roll out. Its initial impact on transmission is really small because not that many people are vaccinated, but it's going to break the link between cases and deaths because the vaccine effort is initially concentrated on nursing homes. It's also going to help keep the healthcare system from collapsing, as the other focus of concentration is on the medical, on the healthcare system. The Biden administration then declares a July 4th victory. It's going to be motivated by these rapidly falling cases. It's going to think that the CDC is no longer shackled into saying crazy things. It's the belief that with vaccines and prior infections that they need about the combination of these two, about 60% herd immunity. The modeling community is really skeptical that July 4th is good. And that's because there are no good estimates of what the fraction of the prior infection is. There's growing awareness the temperature is probably the big explanatory factor for why wave 3 was big. There's growing recognition that the 60% herd immunity level is no longer correct. And what drives that, if you just plug in alpha's R naught of 4, instead of needing 60% of the people to be vaccinated or infected, you need 75%. The Biden administration folks actually made a much more complicated calculation that I'm not really going to get into, which says a lot of the current modeling is trying to get the susceptibility fraction right. So what happened there is that the number of people heard was that your chance of getting serious illness or death if you got vaccinated with Pfizer or Moderna was, in the mid 90s. The number that mattered here was that you had an 80% chance of not getting infected. And so anyway, you can make sort of an overly optimistic one that the Biden administration set a target of 70% vaccination. And anyway, when they put in the estimates of what they thought the past immunity was, they thought they were going to hit about 71%, and people thought that was too optimistic. The other problem that happens is that this is a state-by-state battle. So California's up here is good. There are lots of states that are good. Vermont's 85%, but we have lots of states that are bad. And as long as these bad states are out there hanging around, these states are basically pools that are going to, you know, as soon as the temperature drops, they're going to basically spread the infection. The fourth wave starts right after Labor Day in the usual fashion. High exposure events coupled with mobility, increased mobility and reducing barriers. It's an interesting fight that people don't remember. The UK's Alpha variant is fighting with India's Delta variant, which is oriented toward increasing infectiousness, and fighting with South Africa's Gamma version, which is oriented toward increasing susceptibility by evading prior infections. The temperature response profile is going to drive a peak, the Delta peak, just like it did the prior year. And so the Delta is going to basically, the combination of the temperature amplification and the variant amplification means Delta is going to win. We put out some predictions. This is just, you know, the states that basically got hit first. Alaska's not on the map, but it got hit first. Idaho, you can sort of see the deep red. It then spread across the top states, but it also spread down the Rocky Mountain states and in there. And so the only difference was, what you could see is that states like Idaho that had a low vaccination rate had crisis standards of care declared in its hospital, and Vermont, which had a high vaccination rate, basically was having lots of cases, but very little in the way of deaths and hospitalizations. One way to look at this is that the temperature, that this is a graph of what the herd immunity needed is, and we've used 31C, let's just call that August. And what you can see is that the herd immunity level here for, say, the District of Columbia with alpha is at 75% because it's almost exactly 89 degrees. Delta is going to increase that in August by an R0 addition of 1. But you can see that as you move away from August, that the effective R0 here is going to go way up. And so instead of, you know, what's going to happen in a lot of places, instead of needing 75% vaccinated, as it gets cold, you're going to need 95% vaccinated. And that's equivalent to throwing all those people onto the possibility of getting infected. Okay, so we get the Omicron peak that comes. It infects as many as 50 million people during its run. Anyway, sorry, let's see. Delta is going to lose. Omicron is South Africa's new challenger, and it's going to lose Delta is going to lose out to it. It combines some of Delta's increased infectiousness with some of Gamma's ability to evade infection. It's often referenced as having an R0 of 7, but in reality, if you were to take somebody who was uninfected and unvaccinated, Delta and Omicron are just about the same. So anyway, the TRP is going to amplify things in the whatever, and the combination of being able to evade in the people who were previously infected, it evaded the people who were vaccinated, but at a much lower rate. So pretty much we were infecting millions of people a day. So Johns Hopkins put out a study that said they thought susceptibility was down to 27% with Omicron. That's still a huge number of people to burn through. So we're going to keep burning through people. So what's going to happen is mechanically ST is going to drop, because once the people are infected, they can't get infected again. Boosting is going to decrease ST, because what's happening is that the ability to ward off infection was waning. And slowly, you're also getting up the fully vaccinated rate, and so that's going to decrease ST. So cases fall first, then hospitalizations, and all of this sort of strongly interacts with this. And so what's going to happen as the positivity rate falls, breakthrough infections among the boosted are going to come rare again. And the way to think about that is RT is conceptualized as what happens as a single person got infected. That means that there are really two factors going on. What's your chance of being infected by an infected contact, and how many infected contacts you are. And so the main thing that was driving up people's risk was that the number of infected contacts was going way up. And so that's the difference between the statement that you were more likely to get infected during Omicron was true, but it was true because the number of people who were infected were up, not because Omicron was inherently more infectious than Delta. So let's end this story. The US pandemic is going to come to an end by this 4th of July. And why is that? There are not many people left who are unvaccinated, who haven't been vaccinated or infected or both. And the vaccinated boosted fraction keeps going up. So what this means is that the virus is going to become endemic because of its higher R0 and its much higher infection fatality rate. Means we should be treating it more like measles than the flu, although they'll probably give one shot that combines both. And why am I saying that the pandemic's coming to an end? In general, the pandemic's coming to an end when you hit the high end of herd immunity. But the other way to think about this is that your infectiousness wanes. Your ability to ward off the infection wanes way before your ability to ward off serious disease and death. And so it's unlikely that the hospitals will ever get overwhelmed again. So let's compare, because they're directly comparable, the last month of Trump, 12/21/20 to January 20th. What we had was a little over 6 million cases, almost 90,000 deaths. So when the Biden administration during the same time period faced 18,000 cases and suffered 47,000 deaths, 18 million cases. And that's a 5-fold decrease. So this is the drop in the death rate. So the pandemic has radically changed here over time. A different way to end this story is to say, what did the Biden administration achieve? And you can see that if you had faced Omicron to begin with and had an infection fatality rate of 1.9 from the Diamond Princess, then you were looking at an expected death count of 5.4 million. A more conservative one says the R0's 5, and the lowest credible estimate of the infection fatality rate's about 9.9%, and that's going to yield 2.4 million deaths. So you can say that, how many people did we lose? Roughly 1 million. We're almost at 1 million now. By the time we hit the 4th of July, we'll be a little over 1 million. About 200,000 of those needlessly died during wave 3 when the right strategy was to wait for a vaccine. About 300,000 plus died during wave 4 because they weren't vaccinated in states' reduced barrier methods. But in the end, you can say, what did the Biden folks achieve by the vaccination campaign and the huge effort on face masks and other things? And that is, they saved 2 to 5 million people that you would have expected at the beginning to have been lost. And I'll stop there. And I'm happy to answer questions. They probably have gone longer than
Thank you very much. Sorry, I was muted. Yeah, we're going to use the. That was a fascinating, somewhat long but fascinating talk, an interesting story about the virus. We're going to use the raised hand method for asking questions. So please, somewhere on the bottom of your screen or the top of your screen, depending on your device, you'll see a symbol of a raised hand, and that's what you click on if you want to ask a question. So the very first question will be Christine Sullivan. Please unmute yourself.
Yes, thank you. Yes, thank you for this. I can't possibly pretend to have followed it all, but it was a really interesting look back over what we've all been through and everything. I'm hearing or reading concerns by current people such as yourself about what's coming next. Not so much maybe even related to COVID, although it certainly could be. But we know this isn't, you know, the last plague we're ever going to see, especially with some of the offshoots of global warming that could make these sorts of things more common. So I'm wondering if you know what we're doing to prepare for that, if we can, and if that's even sort of a realistic thing.
Certainly, there's a lot more you can do to prepare. And the surprising thing is that it's a very prominent economist a while, you know, sort of long before this pandemic happened, but in the not that distant past, said, of all the sort of crises that you could think of, ranging from financial meltdowns to climate change, which one would have sort of the biggest sort of short run effect? And pandemics just always jumped out at the top. The fact that we didn't have massive amounts of N95s and other things to deploy, and that we had a health reporting system that was incapable of reporting basic statistics for, you know, almost a year and a half. All of those things could be fixed. I mean, every time Bill Gates talks, you know, pandemics are sort of at the top of his list. Specifically with regard to global climate change, the things that have emerged more recently is the Zika virus actually moved north, and that was clearly a climate change induced notion. People have studied Ebola, and I did some work earlier on Ebola. You know, that's a disease that comes out of the tropics as the temperatures warm. So yes, anyway, we will indeed have another virus. It's just a matter of time, and there are way better ways. There are way better ways to be prepared. So, you know, you can look at countries that were really successful, like New Zealand, and that was the ability to basically detect it quicker, a willingness to implement a really hard lockdown when they see it. But almost every country that has weathered it, almost every country that's basically stopped its economy has weathered it better. And so the economists, when they look at it in retrospect, say, you know, a better initial defense would have saved a huge number of lives and done wonders for the economy. So hopefully this will be a wake-up call.
Fair enough. Jonathan?
Next.
So obviously changes in the global, the number of people, the total population of the world increases the contacts for any kind of virus or any kind of pandemic. And we have some statistics on the rate at which the population is increasing. So what does that say about the probability of upcoming pandemics
Well,
compared to the past?
What's happening is, so the population's increasing. The population density, particularly in big coastal cities, is increasing, and it's actually the population density here which is driving the contact rates. I'm doing work in a number of four African countries right now, and I'm going to say high temperatures and low contact rates have kept things way more in check. So these high contact rates are a feature of modern society. And you can see some terrible circumstances. So a lot of people who work on this think that India lost over 1 million people when it implemented a variant of a lockdown and because it couldn't supply people with basic necessities. It sent people home on tightly packed trains, and then they spread COVID throughout the rest of India from a few of the bigger cities. So yeah, I mean, there's a lot of good work that's going on and continuing to go on to look at the actual sort of network methods by which transmission spreads, and hopefully that will do better. I mean, you know, to a first order approximation, if they had a massive number of N95s in the warehouse and FedEx those, or, you know, express mailed those to everybody within a couple days after they had located it and they locked down, they could have defeated the virus. And what you have to think, and I will say my economic colleagues sort of missed this, although this is where the folks who study the genetics of viruses, they missed how big the variant effect would be. So every time the virus transmits, it basically has a chance of mutating in a way that's not good. And that's a function of population and population density.
Oh, let me ask a question then. So you sound very optimistic about this coming July, but isn't it also the possibility that another variant can emerge, which will be less kind to the vaccines?
Yeah. So one of the things that are to keep in mind is that in terms of the infectiousness of the virus, it could get a little bit more infectious, but with a little bit of temperature amplification, we're up there in the measles sort of range. So what that suggests is that the variants will more evolve in the direction of evading past infection or vaccination. And that's what will keep it pandemic. I should say epidemic rather than pandemic. It won't be able to burn through the country at a hugely fast rate because there's too much immunity. And in that regard, it looks like the immunity, particularly from boosting, is really good. And the people who've been boosted and infected have tremendous protection in lots of different ways. That just, you know, that will just slow it down. And the thing is, if you're not killing a lot of people and you're not overwhelming the hospitals, then you'll get something that looks much more like the swine flu, which turned out to be, you know, that was a virus that had an initial R naught in the range of 2. So not as infectious as COVID, not nearly as infectious as the current variants of COVID, but it didn't cause much in the way of illness. So it ran through the population and infected, you know, 60 to 100 million people without doing a lot of harm. And so what we will see repeat variants of that. I mean, that'll be what it looks like. And, you know, when it evades the virus in such a way that kicks up the illness, you'll see really, really bad flu seasons related to COVID, but nothing like sort of the current
thing.
world yet.
Okay. Are there any other questions?
Well, I have John Bamber has one.
Yeah, Don? Could you unmute yourself, Don?
I don't understand things I read in the popular press that say that a new variant of COVID will drive out an old. I don't understand why they don't just run in parallel.
You know, I mean, let me say your intuition there is exactly right. They often do run in parallel. So if you look at these numbers, and in fact, the CDC puts out a mixture of what the variants out there are, and sometimes they're reasonably localized. I mean, if you were to look at South Africa, for whatever reason, South Africa is where you've generated variants that are good at evading prior infection. So the variants often coexist. If a variant takes a big enough jump in terms of how infectious it is, it's again just sort of an exponential growth sort of notion. They will match each other for a while, and then the one that's basically faster in terms of having a higher probability of infecting somebody will win out. And so anyway, there is indeed almost always a period where they compete. And it's just that the faster one, because it's replicating at this sort of exponential rate, wins out. And how much faster it's replicating determines how long it takes to win.
Dorothy?
Well,
And let me say that the process while this is going on provides the ability for the different variants to basically combine with each other, and that's what Omicron did in South Africa.
Yeah. Dorothy?
okay, well, I'm a big fan of public transportation because of the energy problems and global warming and so on. But clearly, when you were talking about the difference between Los Angeles and New York, for certain types of disease transmission, public transportation can be a problem. So I'm trying to think of ways that one can make public transportation safer. And I think of ventilation systems in the buses or trains. But then you start drying out the mucous membranes of people, and then they probably become more susceptible for that reason. So what do you think can be done? Overheat?
Well, certainly the ventilation systems do a lot. The really surprising thing is how little transmission goes on airplanes.
Mm-hmm.
And indeed, when you trace episodes where there've been multiple people infected on an airplane, and you can do the genetic sequencing. You want to know where you trace the infection to?
The crew.
The bathroom.
Oh.
The space is much more combined, and people take off their masks.
Oh, okay.
There's a great South Korean study of these people who were completely unrelated to each other and not sort of sitting in close proximity. And you could see that they all picked up the sort of same, somewhat funky strain. Yeah. And you could show that they all used the bathroom, and they took off their mask. And anyway, it builds up, and the ventilation in the bathroom is different. But anyway, at least with any airborne virus, I do think this showed that the notion of ventilation was just really important. One of the things, and it's unclear that it will always be true, but they could have early on moved lots of things outside. In other words, church services, once you put them outside, didn't really transmit. And so anyway, so a lot will be learned from ventilation from this. And so that is something that, you know, that at least I don't know about places like India but in the US, they will get the ventilation right, at least in the subway systems and probably the buses.
Let me ask another question. Just as I recall, in the beginning of this pandemic, people were talking both about the transmission through the air, yes, but they were also talking about transmission through surfaces, and there was a lot of concern about you know, you bring home the groceries and you leave them somewhere. And then it's all disappeared somewhere. And
so that was a matter, I should say, of not knowing. And it's fascinating because in other work I've done, there was clearly a group in the US, and it also appears in other countries, that were big into hand washing. So it's sort of there was a group of people who really wanted to engage in hand washing. And so when you didn't know exactly how the virus was transmitting, the hand washing stuff and the pizza boxes really took hold. But you know, this is out of my wheelhouse, but retrospectively, you looked at how much was going on with surfaces, and even like keypads at the grocery stores that they were wiping down for a while. None of that showed any real transmission.
wow, okay.
Via that path. But the problem there was, you know, you're able to detect the virus on the pizza boxes, and you're able to detect the virus on surfaces, but they just, you know, and there may be there's certainly things that transmit, you know, via touching. So, but this was, not only was this an airborne virus, but it also was one that aerosolized, which made it even worse in terms of transmitting. And so something that's got that effective of a transmission mechanism, it doesn't need pizza boxes.
Got it.
But
Okay.
a classic example, the other direction, are some of the common colds caused by the rhinoviruses.
Yes.
And in those cases, you put a bunch of freshmen together in a room playing cards. If one of them is infected, it's much more likely to be transmitted if they're playing cards and are touching something. So it does depend on the virus.
Yeah, no, it depends. And what was interesting, influenza is more influenced by humidity than it is temperature. It's influenced by both. But so that, you know, that is just a characteristic of the individual virus. So it's, you know, it's not, I don't know that there are any great lessons that can be drawn from COVID versus the next virus.
Yeah.
How big of a factor was the level of vitamin D in people who got infected?
You know, I'm going to say the sort of work that I did, and you know, other people who are into what we would call large-scale epidemiological modeling, we just can't tell you. That's not saying there are not medical people out there looking at things like that. So what you need there is the data that everybody wanted and it's really unclear why it wasn't deployed during the Trump administration. The standard thing you would do is you would say, hey, the government is going to go out there and basically swab 100,000 random people, with a sampling design. And, what you really need to look at whether there were particular factors like, vitamin D or particular genetics or whatever that protected people or made them more susceptible. You have to have that individual level data. And so there may well be factors out there that made, particular individuals more or less susceptible to the virus, and if they got it, more or less susceptible to being seriously harmed. But anyway, the sort of thing that I presented here is just, it's all based on sort of big average taking the population as a whole. We control for those things that we can get from the Census Bureau. Those are like gender and age and percent Black.
Did any nation do that? Denmark, for example.
Oh yeah. No. In fact, a huge amount of what we know actually comes from the Scandinavian countries, where they have these very good health registries, and that was why you had all these sort of idiot commentators. Omicron is so much more infectious, and the Danes actually have a study that showed that if you were uninfected and unvaccinated, Delta and Omicron had exactly the same effect. The only thing that was happening was that Omicron was infecting people who had prior infections. Otherwise, in terms of their just sort of base infectiousness, they were exactly the same. And in that regard, the variants let the US public health establishment get by with a lot of stuff that was just, retrospectively wrong. And that was because you didn't know. But these Scandinavian studies where they've got this detailed, sort of information, but after a while it got hard to find uninfected, unvaccinated people. That was just sort of how there.
You mean in Denmark, it was hard to find unvaccinated, uninfected?
Yeah.
Okay.
Actually. Well, anyway, thank you so much. This was fascinating detective story on
Yes.
COVID. And so we appreciate very much you giving us that tour.